Tutorial number 6 in OpenCV. In this tutorial, you're going to need to Google OpenCV, and then we're going to click on Tutorials. And we're going to go down to the core functionality, basic building blocks of the library, and click on that. Then we're going to go down to changing the contrast and brightness of an image. And then we're going to go down the code and click on Python. In the last tutorial, we went over the theory for changing the contrast and brightness of an image. In this tutorial, we're just going to run the code. So we're going to click on Python, downloadable code, click here. We're going to copy the code and hit Control-C to copy. So now we're going to go to PyCharm. Okay, we're going to hit Control-V for paste. And you're going to need a picture, that you want to change the contrast and brightness of. So what I did was I have a picture of a lighthouse that I took, and I'm going to drag that from my desktop into the Python project. So you see it pops up here, but you're going to need your own picture. I'm going to hit the run button in Python, and there's an error line 13, so let's click on that error. So we're going to change this line of code to the name of the file. So we're going to use quotes, and we're going to use lighthouse.png. That's the name of our file, and it auto-populates. So now it should run. We're going to hit run. It says enter the alpha value. I'm going to use an alpha value of 1.3 and a beta value of 40. So 1.3, enter, beta value of 40, enter. And now you'll be able to see before and after. Okay, so the before and after are now appearing on the screen. So before, you can see it's darker and there's not as much contrast. We're going to hit back again. And now other tutorials, machine learning, object detection, photo stitching, and video. So we're going to do object detection in the other tutorials. So we're going to click on that. And we're going to click on under object detection, Cascade Classifier, and click on that. So Cascade Classifier goal. In this tutorial, we'll learn how to use the HAR Cascade object. We will learn how the HAR Cascade object detection works. We'll see the basics of face detection and eye detection using the HAR features-based Cascade classifiers. We'll use the CV Cascade classifier class to detect objects in a video stream. Particularly, we will use the functions CV Cascade classifier load to load an XML classifier file. It can either be a HAR or LBP classifier. CV classifier, Cascade classifier detect multiscale to perform the detection. Theory, object detection using HAR feature-based Cascade classifiers is an effective object-based method proposed by Paul and Michael Jones in their paper, Rapid Object Detection Using Boosted Cascade of Simple Features in 2001. It is a machine learning-based approach where a cascade function is trained from a lot of positive and negative images. It is used to detect objects in other images. Here we will work with face detection. Initially, the algorithm needs a lot of positive images of faces, and negative images without faces to train the classifier. Then we need to extract features from it. For this, the HAR features shown in the below image are used. They're just like our convolutional kernel. Each feature is a single value obtained by subtracting sum of pixels under the white rectangle from sum of pixels under the black rectangle. So here, A is edge features, B is line features, and C is 4 rectangle features. Now, all the possible sizes and locations of each kernel are used to calculate a lot of features. Just imagine how much computation it needs. Even a 24 by 24 window results in, let's see, 160,000 features. For each feature calculation, we need to find the sum of pixels under white and black rectangles. To solve this, they introduce the integral image. However large your image, it reduces the calculations for a given pixel to an operation involving just 4 pixels. Nice, isn't it? It makes things super fast. Among these features we calculated, most of them are irrelevant. For example, consider the image below. The top row shows 2 good features. The first feature selected seems to focus on the property that the region of the eyes is often darker than the region of the nose and cheeks. The second feature selected relies on the property that the eyes are darker than the bridge of the nose. But the same window applied to the cheeks or any other place is irrelevant. So how do we select the base features out of 160,000 plus features? It is achieved by ADIA boost. For this, we apply each and every feature on the training images. For each feature, it finds the best threshold, which will classify the faces to positive and negative. Obviously, there will be errors or miscalculations. We select the features with minimum error rate, which means there are features that most accurately classify the face and non-face images. The process is not as simple as this. Each image is given an equal weight in the beginning. After each classification, weights of misclassified images are increased. Then the same process is done. New error rates are calculated, also new weights. The process is continued until the required accuracy or error rate is achieved or the required number of features are found. The final classifier is the weighted sum of these weak classifications. It is called weak because it alone can't classify the image, but together with other forms a strong classifier. The paper says even 200 features provide detection with 95% accuracy. Their final setup had around 6,000 features. Imagine a reduction from 160,000 plus features to 6,000 features. That is a big gain. So now you take an image, take each 24 by 24 window, apply 6,000 features to it, check if it is a face or not. Wow, isn't it a little insufficient and time consuming? Yes, it is. The authors had a good solution for this. In an image, most of the image is non-face region. So a better idea to have a simple method to check if a window is not a face region. If it is not, discard it in a single shot and don't process it again. Instead, focus on regions where there can be a face. This way, spend more time checking possible face regions. For this, they introduced the concept of cascade of classifiers. Instead of applying 6,000 features to a window, the features are grouped into different stages of classifiers and applied one by one. Normally, the first few stages will contain very many fewer features. If a window fails the first stage, discard it. We don't consider the remaining features on it. If it passes, apply the second stage of features and continue the process. The window which passes all stages is the face region. How is that? That is the plan. The authors detected 6,000 plus features with 38 stages with 1, 10, 25, and 50 features in the first 5 stages. The 2 features in the above image are actually obtained as the 2 best features from ADA boost. According to the authors, on average, 10 features out of 6,000 plus are evaluated per sub window. So this is a simple, intuitive explanation how the Violetta-Jones face detection works. Read the paper for more details or check out the references in the additional resources section. So in the next tutorial, we'll finish reading about the HAR cascade detection and OpenCV below, and we'll run the code in Python. That's all for today. Thank you for watching. If you liked what you saw, please give a thumbs up. If you have comments or questions, please make them.